The students who have recently joined, I would like to repeat that you should start with the first problem and try solving it yourself. The sir would join in a bit. So you can try to solve the first problem. It's simple. Any doubts till now? Were you able to solve the first part of the first problem?
Sir, can you please confirm the answers for the first question?
Yes. What's the first part?
So first part is maybe 1.25 L.
What? 1 point?
1.25 times the original length, the
Of,
thickness.
of part 2.
Question 1 part 1 and the second part 25%.
Okay. I would just confirm them. Any other answers? The people who have solved the first question can move to the next question now. So the answer to the first part of the first question comes out to be 75%. That is 1.75 times the length. And to the second part of the first question, the answer is 0.25. That's If you people are not able to solve, not a problem. Just give it a shot. The professor is going to join within 5 to 10 minutes because he was busy in a meeting. So just give it a try to the both the problems. Okay.
And if someone has solved the second question, they can tell us the answer they've got.
So is the answer 0.599?
Yeah, right. It's 0.6. Others also try, and please let us know if you get the same answer.
Hello everyone. Hello. Can you hear me?
Yes, sir, you are audible.
Okay. So have you got this tutorial sheet? Did you get the tutorial sheet? Hello.
Yes, sir.
Okay.
Yes, sir.
Okay. So let me just go through the solution of the tutorial sheet. If you all have tried so far, I have asked the TAs to continue in between because I had a meeting with director, so that's got delayed a little bit. Anyway, let me just share the Can you see the whiteboard? Hello.
Yes, sir.
Yes, sir.
Okay. So in these particular two questions, I will just go through the problem statement of the first question. The first question is, a wall has two layers of insulation on it. The layers are of equal thickness, but the thermal conductivity of the layer is twice that of the layer 2. How much more thicker should layer 2 be if the heat flow is to be reduced by 20%? The total wall thickness and the driving force remaining unchanged. So that is part 1. And part 2 is, what would be the fractional reduction in heat flow if the material of layer 1 is replaced by material of layer 2? So what is being asked in the problem is, there is a composite wall is there of layer 1 and layer 2, and both the layers are of equal thickness. Let's say the thickness of each layer is small l. So as I have shown here, this is the same tutorial answer script which I have done in the last tutorial class yesterday. So the same tutorial, the answer script which I have made at that time. Okay. So there is a layer 1 and layer 2. Both are of having the same length L. Again, the thermal conductivity of the layer 1 is K1. Similarly, the thermal conductivity of the layer 2 is K2. Okay. Now what is been given in the problem is, the thermal conductivity of the layer is twice that of the layer 2. That means K1 is equals to 2K2. That is what is been given. Okay, correct. Now in part 1, what is been asked is, how much more thicker should layer 2 be if the heat flow is to be reduced by 20%? So let us assume that the rate of heat flow is, let's say, Q in this first case, where the length of both the layers is L. And since in the problem it is given that the rate of heat transfer is reduced by 20%, that means the new rate of heat transfer is going to be 0.8 Q. The thickness of layer 1 is reduced some amount, but by keeping total layers twice. The first case is given by this equation. This is the same equation which we have seen earlier, isn't it? So the driving force is delta T divided by the individual resistances of each layer. So resistance of first layer is going to be L by K1A plus the resistance of second layer is going to be L by K2A. The thickness of both the layers is same as L. Okay. Now in the second condition, what is given is, the rate of heat transfer is reduced by 20%. That means the new rate of heat transfer is going to be 0.8 Q. Isn't it? The new rate of heat transfer is 0.8 Q. Now the question is, how much should be the length of the layer 1 and layer 2? That what is being asked. Okay. So the constant to twice L. Whereas in the second condition, let us assume that the thickness of the layer 1 is X, and therefore the thickness of the layer 2 is going to be 2L minus X, because the total length of both these slabs is going to be 2L, isn't it? So the thickness of the layer 1 is going to be X, thickness of the second layer is going to be 2L minus X. So we can put it in this equation. So this equation can be rephrased as 0.8 Q is given as delta T. So delta T remains as it is. That is what is been given in the problem, isn't it? Driving force remains the same. That means delta T is the resistance of the first layer is X by K1A. So that is what is been given here, X by K1A in equation number 2. That is the resistance of the first layer. We are assuming that the thickness of the layer 1 is reduced, and therefore the layer will be by amount in order to have the total length constant to 2L, and therefore the resistance of the second layer is going to be 2L minus X divided by K2A. Again, what is being given in the problem is K1 is equals to 2K2. So K1 2 here in this equation. So you will get equation number 3. And similarly, equation we can replace this K1 by 2K K2. So that becomes equation number 4. Okay. So are you all able to follow whatever we are doing so far? Hello? Hello?
Yes, sir.
Are you all able to follow what we are doing?
Yes, sir.
Okay. So now we got equation number 3, which is for condition 2, when the rate of heat transfer is reduced by 20%, whereas equation number 4 represents the initial condition when the length of both the layer is L, isn't it? So we can take the ratio of equation 3 and 4. So this Q will get cancelled out. We will get 0.8 here. This delta T will also get cancelled out. So what we will have in the numerator is going to be L by 2K2 plus L by K2 and divided by X by 2K2 plus 2L minus X by K2. So here K2 is also common. Just wait. Okay. So this K2 is common in all numerator as well as denominator terms. So this K2 will get cancelled out. So what we get in the numerator is L by 2 plus L divided by X by 2 plus 2L minus X. So and that is equals to 0.8. So we can rearrange this and we can find out how L is related to X. So what we get by rearranging mathematically this is X equals to 0.25 L. So what it means is, in order to reduce the rate of heat transfer by 20%, my thickness of the first layer is going to be reduced by 75%, isn't it? Whereas the thickness of the second layer is going to increase by the 75%, isn't it? That is what it means. X is 0.25 L. That means it is reduced by 75%, isn't it? So are you all able to follow what we are doing?
Yes,
Can
sir.
we go to the next part?
Yes, sir.
Okay. So this is the answer of part A, part 1. Okay. What was the second part? In the second part, what has been asked is, layer 1 is completely replaced by layer 2. If the layer 1 is completely replaced by layer 2, how much will be the reduction in the rate of heat transfer? That is what is been the question. I can go up and we can again see the statement here. You can clearly see in the second part what would be the fractional reduction in the heat flow if the material of layer 1 is replaced by material of layer 2. So in the second part, what has been asked is, layer 1 is completely replaced by layer 2, and by doing that, how much will be the reduction in the rate of heat transfer? That is what the question is. Okay. So based on this condition, again we can write down the equation for rate of heat transfer, that is given as Q dash, and Q dash is given as delta T divided by 2L by K2A, because now both the layer 1 and layer 2 are of the same material of layer 2, and therefore the total length is 2L, isn't it? Thermal conductivity is K2, and again in all these equations we are assuming the cross sectional area equals to 1, isn't it? Cross sectional area we have assumed 1. That is what I have at the top. If you don't assume this, you will get the answers per meter square. The answers will be per unit area. Okay. So again, we can put all the values here. Just you can divide this entire thing. You can divide the equation number 5 by again equation number 4. Equation number 4 is this, the original condition number 1, isn't it? So this delta T will get cancelled out. K2 and this K2 will get cancelled out. The area A is common for all the layers, so that will also get cancelled out. So what we are left with is L by 2 plus L divided by twice L, isn't it? We can rearrange this. So after rearranging, what we get is 3 by 4. So Q dash by Q, where Q dash is nothing but the new rate of heat transfer when we replace the layer 1 by layer 2, then the net rate of heat transfer is Q dash. So Q dash by the original Q is going to be 3 by 4. That means what? That means what?
It is reduced by 25%.
25%. Correct. The heat loss is going to be reduced by 25%. Correct. Yes. So this is the answer for the second part. Now let's move to the second question. Okay. So I have purposefully selected a simple questions in this particular tutorial because this is the first tutorial. The questions are going to be a little bit more complicated as we move along. Okay. So now the second question is, a hot chamber has an 8 centimeter thick inner layer of fire brick. Thermal conductivity is given as 1.04 watt per meter degree Celsius and 30 centimeter outer layer of ordinary brick. The inside and outside surface temperatures of the composite wall are 400 and 75 degrees Celsius respectively. Considering that the outer surface temperature is too high, it is decided to apply a 5 centimeter thick layer of plaster on outer surface. On doing this, the outer skin temperature is reduced to 60 degrees Celsius and the rate of heat loss decreased by 250 watt per meter square. Yeah, calculate the thermal conductivity of the layer of the plaster. Okay, so now what is been given in the second problem is a inner layer of fire clay and then there is the ordinary brick outside. So this is a classic example of a composite wall. So inner wall is of, outer wall is of a ordinary brick. The temperature along the inner wall is 400 degrees Celsius. The temperature outside the outer wall is 75 degrees Celsius. But this temperature of the outer wall is considered to be little bit higher, and because of that a additional layer of plaster is added, and because of this addition of this plaster layer the heat loss is reduced. So whatever the heat loss we had earlier, that is reduced by 250 watt per meter square, and also the outer wall temperature is reduced to 60 degrees Celsius instead of earlier value of 75 degrees Celsius. The layer of plaster which we have added outside the ordinary brick, that layer is of the thickness 5 centimeter. So calculate the thermal conductivity. We have to calculate the thermal conductivity of the plaster layer. Okay. So again, in this case, we have two walls, two layers are there. So we can write down the rate of heat transfer directly here. So rate of heat transfer will be written as Q is given as Ti minus T naught, where Ti is the inner temperature, T naught is the outer temperature. L1 by K1A is nothing but the resistance of the fire brick layer. L2 by K2A is nothing but the resistance of the ordinary brick layer. Again, we can put all the value. Ti is 400, outer temperature is 75. So 400 minus 75 divided by L1 is 8 centimeters. So that becomes 0.08 divided by K1A. So here the thermal conductivity of the fire brick is 1.04. And again, the area we have assumed to be 1 meter square. So unit area we have assumed. So the first layer resistance becomes 0.08 divided by 1.04. Similarly, the thickness of the second layer is nothing but the ordinary brick layer. So the thickness of the ordinary brick layer is 13 centimeter. So that becomes 0.13 meter divided by 0.69. So 0.69 is the thermal conductivity of the ordinary brick layer, and the area is same as 1 meter square. So by putting all these values and calculating, what we get is Q comes out to be 1225 watt. Okay. So this is what we have obtained, the net rate of heat loss from the outer wall. Okay. Now what is been given in the problem is an additional layer of plaster is put on the ordinary brick. This additional layer of plaster is of 5 centimeter thick, and by putting this, the rate of heat transfer is reduced by 250 watt per meter square. So this whatever the rate of heat transfer Q we have obtained equals to 1225, that is reduced by 250 watt per meter square, isn't it? So that becomes Q, the new rate of heat transfer comes out to be Q minus 250. So that becomes 975 watt. Okay. Again, the temperature is reduced to 60 degrees Celsius, isn't it? Earlier temperature was 75 degrees Celsius. So again, we can write down the rate of heat transfer equation. So Q dash can be written as T minus T new, T outer new So that becomes 400 minus 60 divided by the summation of all the individual resistances in layer 1, layer 2 and layer 3. So layer 1 we already have discussed, that is 0.08 divided by 1.04. Layer 2 is 0.13 divided by 0.69. And the third layer, the thickness of the third layer is 5 centimeters, so that becomes 0.05 divided by thermal conductivity K, and the area is equals to 1. So that becomes 0.05 divided by K, and this entire thing is equals to 975. 975 is the new rate of heat transfer. So in this particular equation, the only unknown is K. Only unknown is K. So we can calculate the K from this. Okay. Calculate the value of K. Calculate the value of K. Hello. So what is the value of K? Anybody?
0.59.
Okay, so after calculating, what we get is K comes out to be 0.59 or 0.6. Both are correct. Watt per meter degree Celsius. So this is the thermal conductivity of the plaster layer. So this is the answer of second question. So are you all able to follow?
Yes, sir.
Hello. Are you all able to follow? Is there any question?
Yes.
Is there any question?
No, sir. Fine.
Okay. So can we stop here unless you have any questions? This is the answer of second question. Can we stop here?
Yes, sir.
So unless you have any doubt or any question, we can stop here. Again, there are two TAs, Aditya and Siddharth are the two TAs for this particular course. Whenever such emergencies are there, probably they will be, helping you guys to solve the problems. Otherwise, if you ask all your seniors, mostly the tutorials are conducted by me. But you can take the help from them. They have already done the course earlier. So if you have any doubt, anything, you can ask them also. There is no problem. Okay. You can ask me also. There is no problem. You can ask me. You can ask the TAs. And in general, I want students to solve the problems by their own. And it's really difficult to monitor here online. But otherwise, I used to monitor each and every student in the offline tutorial classes. But that seems to be, a little bit difficult here. Okay. Of course, I will give you the solution at the end. But I want you guys to make the effort from your side for solving the questions, because then it is going to clear a lot of your doubts, isn't it? Whenever we see the solutions, then the problem seems to be easy, isn't it? But when you will have to solve by your own, then it becomes really difficult. So this is one of the comment I regularly see in my assessment, that generally the students say the tutorial questions are easy, exam questions are difficult, but that's not the case. You will find that for tutorial questions I generally give the solutions, and that's why this question seems easy, but the questions given in the exam, these are you will have to solve directly, isn't it? So therefore you find it little bit difficult. Okay, so we stop here unless you have any doubt question, and please try to solve the questions in the tutorial class. Of course, I'm going to give you the solutions at the end. Okay. So we stop here. Let me unshare this. And thank you. See you on Thursday then.